was simple enough that you could replace y in terms of x relatively easily. But let's say if instead of perimeter being fixed, the equation was something more complex, like let's say x plus y plus sine x plus cos y equals to 0. So now you can see that you can't really replace y in terms of x anymore, right? And so that approach doesn't work all the time. And so we have to come up with a more rigorous way of figuring out how do you optimize when you have a constraint, okay, without the substitution. Make sense? Okay, so let's try to figure out how to do that. So first, let's just graphically try to understand what this whole business means of constraint optimization. So right now we only have g as a function of x comma y. Now I want to, so let's plot this constraint g as a function of x comma y. And let's say this constraint looks something like this, just for simplicity. Okay? So this is x. So g of x comma y equals to 0 on xy plane is basically a curve, right? This curve could be a more complicated shape. Does everybody understand this? G of x comma y basically is what? So y, so in general, if you say think of y equals to f, let's say, so g of x comma y is equivalent to saying y is some function of x, like h of x. I can't use f because f is not the function that we're maximizing. These two are equivalent descriptions. So we see that? Basically, simply g is therefore y minus h of x. Right? So anytime you have a curve in xy space, you can write it as y is some function of x, or a more appropriate way of writing it is as g as a function of x comma y equals to 0. Right? Which may or may not be expressed in the explicit form. This is called explicit representation. Okay? But for many equations, that explicit representation is not possible. So what you have is you have your curve is an implicit equation that relates y and x. Right? Does it make sense to everybody? What it means is you take, for every point of x you take, you get a point of y. You keep putting those points here, and you connect them by a curve, and that's your g equals to 0. Yeah? Okay, so let's say that's how g equals to 0. So what we're saying, so now let's ask ourselves, what do we mean by constraint optimization? What constraint optimization means is that imagine that you're walking along this curve, right? You cannot leave the curve. You have to stay on the curve. At every point, you keep computing the value of f. And you finally figure out where is the f, maximum or minimum. Okay? So in reality, if you look at the entire two-dimensional plane, those points are likely not extremums of f. Because f extremum might lie there, here, somewhere else. But those are not relevant to us anymore because we have to stay on this curve. Does it make sense? Okay, good. So to figure out how to do this, let's start making some curves. So this curve that I'm drawing is, let's say, this curve is for constant values of f. So f is the function you're optimizing. You can always, so you cannot just draw f. Well, you can certainly draw f equals to 0, but if somebody just draw f on a xy plane, you can't draw it, right? It doesn't mean anything. But you can draw f equals to 0. You can also draw f equals to some constant value. So let's say you draw f equals to c1, c2, c3, c4, c5, and so on and so forth. Right? So you can certainly draw curves of constant f. But you, right? And so let's say we have drawn all those curves. So we have drawn curves where f is constant. Okay? You can draw those. And let's say that, well, let's just call this C1, C2, C3. C1, C2, C3, C4, C5. And let's say that C1 greater than C2, greater than C3, greater than C4, greater than C5. Okay? So let's say the value of function is increasing in this direction. F increasing.
You wrote that C1 was the least.
No, opposite, okay. It doesn't matter, but okay? All right. So F is increasing that way. And let's say I'm going to find out the maximum value of F. Okay? All right. So now let's start walking. I'm walking in this point, I suddenly see C1. Okay? So I will see the value of C1 at two different points, here and here. If I keep walking, I see C2. Is C2 larger than C1 or less than C1? Greater than C1. Greater than C1. So I keep walking, then I finally come here, and if so based on this picture, where do you think will be the maximum value that you can, yeah?
At the top of the curve.
At the top of the curve, right? Because as long as you can keep, I mean, I just intentionally didn't draw a curve there, but you can see as long as I keep drawing curve in this direction, the value will keep increasing, right? So the point of maximum is actually tangent to this curve, right? The value of F along that tangent, that's the maximum value of F, subject to this constraint. Yes, make sense? I'm going to give you a minute to digest this and ask questions because, you know, in some sense it's easy, but sometimes it could be confusing. No? Everybody's good? All right. So then let's just figure out what does it mean that these two curves are tangent. If these two curves are tangent, which means they intersect at just one point, mathematically what does that mean?
Slopes.
Sorry?
Slopes.
They have the same slope at the point of intersection, right? Okay. So if you have an equation g of x comma y equals to 0, or f of x comma y equals to some constant c, I'm going to figure out the slope of these.
Take the derivative of them instead of multiples? Or
Sorry?
take the derivative and plug in the point?
Take the derivative of what?
Take the derivative of
Of
g
f of g.
With respect to what?
x.
Of all of them, x, y, z, and z.
Okay, and then what? Now how do you get slope from there?
You have to plug in the point into the derivative that it's at, right?
Oh, but you first have to tell me what slope is. How are you going to compute slope?
Take the gradient.
You can take the gradient, yes, and get the slope from there. But right now, we don't even have to invoke gradient because I don't know how many of you know actually differential calculus. How do you figure out slope on an xy plane? What is the slope of a curve in xy plane? Okay, rise over run. Which is in differential form is, what is rise in this case? What is rise? Y. What is run? X. So the slope is dy dx, right? So slope is dy dx. Okay, so you can't just get dy dx from here, but what you can do is you can differentiate g, total differential, right? So total differential basically means dg, but dg is going to be del g del x dx plus del g del y dy, right? Yeah.
So, like, we can figure out where that's equal to where if you held c constant, then dy dx of that function.
No, c is not constant. C could be any value. C is a number you pick randomly. I mean, not randomly, but you just pick, and therefore you construct the F curve.
That's what we're solving for, isn't it?
Well, right now we are figuring out what does it mean, how to get a slope of the two. So we are really, C will figure out eventually. We are looking for the point where the curves of constant f intersect with, now for certain values of c, there might be no intersection, right? But for the point at which there is a single solution, the two curves are, the slopes are going to be equal, right? And so the slope is dy dx. So from this equation, you can see dy dx is going to be equal to minus del g del x right? Make sense? A lot of times students actually, before if you don't do this correctly, if you don't do it like this, sometimes students make a mistake of putting a positive sign there because that seems intuitive, right? Actually, I can tell you it's not just students. My PhD advisors make the same mistake. I'll never forget that. I was once trying to take some derivative and I correctly had a minus sign because I derived it. They were like, why is there a minus sign? There should be no minus sign. So I could derive for them that you have to get a minus sign. Okay? And actually there's a kind of a reason why there's a minus sign. But I don't want to get into that right now. I mean, mathematically you can see why there has to be a minus sign. Physically also you can argue why there has to be a minus sign. Anyway, so that's how you get dy dx. So therefore, you can similarly get dy dx for the f equation. So you can see the equation you get is the slopes are equal means minus fx or fy equals to minus gx over g. Right? Yeah? So this equation basically tells you that, yeah, the two are tangent. So that's, how many unknowns do you have?